History. The scale used to indicate magnitude originates in the Hellenistic practice of dividing stars visible to the naked eye into 6 magnitudes. The brightest stars in the night sky were said to be of 1st magnitude, whereas the faintest were of 6th magnitude, which is the limit of human visual perception. Each grade of magnitude was considered twice the brightness of the following grade. Although that ratio was subjective as no photodetectors existed, this rather crude scale for the brightness of stars was popularized by Ptolemy in his Almagest, and is generally believed to have originated with Hipparchus. In 1856, Norman Robert Pogson formalized the system by defining a 1st magnitude star as a star that is 100 times as bright as a 6th magnitude star, thereby establishing the logarithmic scale still in use today. This implies that a star of magnitude m is 2.512 times as bright as a star of magnitude m plus 1. This figure, the 5th root of 100, became known as Pogson's ratio. The 0 point of Pogson's scale was originally defined by assigning Polaris a magnitude of exactly 2. Astronomers later discovered that Polaris is slightly variable, so they switched to Vega as the standard reference star, assigning the brightness of Vega as the definition of 0 magnitude at any specified wavelength. Apart from small corrections, the brightness of Vega still serves as the definition of 0 magnitude for visible and near-infrared wavelengths, where its spectral energy distribution closely approximates that of a black body for a temperature of 11,000 K. However, with the advent of infrared astronomy, it was revealed that Vega's radiation includes an infrared excess, presumably due to a circumstellar disk consisting of dust at warm temperatures. At shorter wavelengths, there is negligible emission from dust at these temperatures. However, in order to properly extend the magnitude scale further into the infrared, this peculiarity of Vega should not affect the definition of the magnitude scale. Therefore, the magnitude scale was extrapolated to all wavelengths on the basis of the blackbody radiation curve for an ideal stellar surface at 11,000 K, uncontaminated by circumstellar radiation. On this basis, the spectral irradiance for the 0 magnitude point as a function of wavelength can be computed. Small deviations are specified between systems using measurement apparatus developed independently so that data obtained by different astronomers can be properly compared. Of greater practical importance is the definition of magnitude not that of single wavelength but applying to the response of standard spectral filters used in photometry over various wavelength bands. With the modern magnitude systems, brightness over a very wide range is specified according to the logarithmic definition detailed below, using this 0 reference. In practice, such apparent magnitudes do not exceed 30. The brightness of Vega is exceeded by 4 stars in the night sky at visible wavelengths, as well as bright planets such as Venus, Mars, and Jupiter, and these must be described by negative magnitudes. For example, Sirius, the brightest star of the celestial sphere, has an apparent magnitude of -1.4 in the visible. Negative magnitudes for other very bright astronomical objects can be found in the table below. Standard reference values. It is important to note that the scale is logarithmic. The relative brightness of 2 objects is determined by the difference of the magnitudes. For example, a difference of 3.2 means that one object is about 19 times as bright as the other, because Pogson's ratio raised to the power 3.2 is approximately 19.05. A common misconception is that the logarithmic nature of the scale is because the human eye itself has a logarithmic response. In Pogson's time this was thought to be true, but it is now believed that the response is a power law. Magnitude is complicated by the fact that light is not monochromatic. The sensitivity of the light detector varies according to the wavelength of the light, and the way it varies depends on the type of light detector. For this reason, it is necessary to specify how the magnitude is measured for the value to be meaningful. For this purpose, the UBV system is widely used, in which the magnitude is measured in 3 different wavelength bands, U, B and V. The V band was chosen for spectral purposes and gives magnitudes closely corresponding to those seen by the light-adapted human eye, and when an apparent magnitude is given without any further qualification, it is usually the V magnitude that is meant, more or less the same as visual magnitude, because cooler stars, such as red giants and red dwarfs, emit little energy in the blue and UV regions of the spectrum. The power is often underrepresented by the UBV scale. Indeed, some L and T-class stars have an estimated magnitude of well over 100, because they emit extremely little visible light, but are strongest in infrared. Measures of magnitude need cautious treatment, and it is extremely important to measure like with like. On early 20th century and older orthochromatic photographic film, the relative brightnesses of the blue supergiant Rigel and the red supergiant Betelgeuse, a regular variable star, are reverse compared to what human eyes perceive. Because this archaic film is more sensitive to blue light than it is to red light, magnitudes obtained from this method are known as photographic magnitudes, and are now considered obsolete. 4 objects within the Milky Way with a given absolute magnitude, 5 is added to the apparent magnitude for every tenfold increase in the distance to the object. This relationship does not apply for objects at very great distances, because a correction for general relativity must then be taken into account due to the non-Euclidean nature of space. For planets and other solar system bodies, the apparent magnitude is derived from its phase curve and the distances to the Sun and observer. Table of notable celestial objects. Some of the above magnitudes are only approximate. Telescope sensitivity also depends on observing time, optical band pass, and interfering light from scattering and airglow.